Okay, so welcome everyone. It's great to see so many people on a Tuesday. So it means that our speaker is very popular. So that's great to see you all. So it's a great pleasure today to have Andrew Gettelman. So he was, when we started, part of NCAR. Now he's at PNNL, Department of Energy Lab. He received many awards from the American Geophysical Union, including the Ascent Award. He is also a fellow of the American Geophysical Union. And he's been doing very innovative type of work at the interaction between cloud and aerosol and cloud physics. And we are very much looking forward to having him today. Thanks for coming.
Great. Thanks, Pierre. It's good to be back. It's good to see the place crowded. It's good to see so many people here. So get rid of that. There we go. Now I can see more. Okay. So this is work I've been doing with David John Gagne at NCAR and Wayne, who is here. Where's Wayne? There's Wayne in the back. And Jack Chen also helped us start this at NCAR. And as Pierre said, this started as part of LEAP. There's some NASA funds involved in here and the NSF sponsorship, and I'm now at PNNL, but trying to keep a good collaboration going. So for motivation, I thought I'd just cheat, go ask somebody else. So what is the essence of a climate model? Because that's what we're talking today about, is where we are in machine learning and climate models. So this is sort of boilerplate. Looks like, I don't know, it's probably going to look like Kate Calvin's talk this afternoon, very high level, generic boilerplate. But they're designed to help us understand past, present, and future climates. And the goal is to actually inform decisions on climate change. Fine. I thought I'd get a little more poetic with machine learning. So this is one of my, if you ever listen to the words of Both Sides Now by Joni Mitchell, it starts out and it's all about cloud physics. And it's very apropos. So the images here were generated by Google Gemini, actually. So I actually gave it this text and said, okay, draw me a picture. So rows and flows of angel hair and ice cream castles in the air and feather canyons everywhere. We've looked at clouds that way. But now they only block the sun. They rain and snow on everyone. So many things I would have done like Saturday afternoon, but clouds got in my way. So I've looked at clouds from both sides now, up and down, and still somehow it's cloud illusions I recall, and I really don't know clouds at all. These things are not that actually good at some of this stuff. So you can see where it's starting to hallucinate. This is what it thinks a radar picture looks like. Okay, so back to actual science. This is an actual radar from the ground. That's a satellite. We're not quite there on actually generating artificial images of science data, but at least it told us it was wrong. So there is some hope. At least Google knows when it's hallucinating. So I'm going to talk a little bit about why cloud physics is important. I'll talk about some current machine learning approaches to cloud physics and give an update on what we've been doing in CESM with LEAP, particularly on cloud physics, and then talk about summary and next steps and where we're going. And the bottom line is we've actually been able to take what we've been doing on cloud physics and stick it in the model as an option. So we're actually going to have a machine learning approach in the cloud physics that's released in CESM3 when it comes out in the next year or so. So I usually describe the motivation for cloud physics as being very simple, is that cloud microphysics kills people. If you actually think about severe weather and even climate impacts, almost everything you can think of, with the exception of drought, happens because of clouds: tornadoes, thunderstorms, hail, tropical cyclones. There are important cloud processes involved in all this stuff. And this is just an example of a squall line simulation, which evolves due to the evolution of the cloud physics and the latent heat release. And things like tornadoes are involved, again, with details of cloud physics. So when we get to climate, there's also clouds are very important for a number of reasons, and I'll go into that. The climate effect of clouds is slightly different. The weather effect of clouds usually has to do with the actual precipitation and the latent heat release and the evolution of that, and how water and condensation moves energy around in storm systems in the atmosphere. When we think about climate, it's actually about radiation. And the two things you have to know about clouds are very simple. Clouds are white and clouds are cold. So white is the short wave. Clouds reflect more, and they are usually brighter than the surface underneath them. They reflect more energy to space in the short wave. They cool the planet. Clouds are generally colder than whatever's beneath them when they radiate in the infrared. And so they actually end up warming the planet because they radiate less energy to space than they absorb from the surface. They act like a blanket. So the balance of those two things is important. And the balance of those two things is actually, you can see how important it is. The shortwave cooling is about minus 50 watts per meter squared. The long wave warming is about 25 watts per meter squared. And you can see the long wave is a map of cloud height, and the short wave is a map of where the clouds are white. And you can see there is no shortwave cloud radiative effect over the brightest surfaces, meaning the Sahara Desert and over the ice sheets. The deserts and over the ice sheets, there's no effect of clouds because the surface underneath them is already bright. The net looks like that. It's a combination of those two things. You'll notice that number, which is the difference you get. These effects are the difference between a clear sky and a cloudy sky. That number, if you think about doubling carbon dioxide warms the planet by 4 watts per meter squared. That's 5 times that effect. So small changes to cloud properties can have a big lever on what's going on with climate. The second thing that's important about clouds is they're affected by atmospheric particles, by aerosols. So there are direct effects of aerosols, which are not cloud related. They're just scattering and absorption. But what you get is these aerosol cloud interactions, because aerosols are the places where clouds actually form on cloud condensation nuclei. Water doesn't like to condense in the atmosphere, neither does ice spontaneously. It likes to have help. So you get solution drops, you get other things that can start to form drops that lower the vapor pressure, or particles that actually, like particularly for ice, particles that are shaped like ice crystals that water molecules like to stick to, or freeze on, because water doesn't like to lock into an ice lattice very easily. So what happens is when you increase the aerosols in the atmosphere, you tend to actually get more cloud drops. And versus an unperturbed cloud, 2 things happen, which I've demonstrated here. One of them is that cloud is just physically brighter. It's whiter, reflects more radiation back to space. That's a cooling effect. The other thing is smaller drops don't precipitate as readily. If you take the same amount of water and give it a small amount of drops, the supersaturation gets sucked up to a few drops. They get big, they fall out. You get a lot of drops, they don't. They stick there. They stay around. So the cloud can live longer. It also doesn't precipitate as much. So this can also have some profound effects. And you can see this a lot. This is the Atlantic coast of France up there. And I guess I can use a pointer. This is Brittany and Normandy up here. This is the Iberian Peninsula. This is sort of Galicia and Catalonia up here, or Basque Country up here. And what you see in this shipping lane around the coast of Europe, in an air mass that's susceptible to forming clouds anyway, is when a ship goes by, the heat and water, and especially the particles, and this has been researched, it's not the heat and water, it's the particles out of the ship, actually form essentially like a contrail from the ship in low cloud decks. You're dumping particles into the atmosphere, and they cause condensation, and they cause brighter clouds, and they stick around longer. So this forcing mechanism, these aerosol cloud interactions, is actually really important. This is an IPCC chart showing total anthropogenic forcing. Here's the CO2 warming, long-lived greenhouse gases, short-lived greenhouse gases. You'll notice 2 things. This is the direct effect of aerosols, and this is the indirect effect of aerosols, these aerosol cloud interactions. And you'll notice that this error bar is the largest on that whole chart, and it's a cooling. So this actually, clouds are very important because we don't understand how much we forced the atmosphere, what this total anthropogenic radiative forcing number is over the historical record. And a lot of that error bar is due to these cloud processes. So that's the forcing effect of clouds. The feedback effect is slightly different. We actually can, as I mentioned before, changes to the cloud environment by, say, warming the surface will actually change cloud properties. They don't have to change the cloud properties very much because the clouds are a huge cooling to get a big delta on the warming. A 5% change in the net cloud effect is 1 watt per meter squared. That's 25% of the greenhouse warming. So if you look at the responses of the atmosphere to, or the feedbacks of the atmosphere to warming the planet, you get a chart that looks like this. And the first one is the Planck effect. If you warm up the planet, it's a black body, it radiates more to space. That's just sigma t to the 4th. That's a huge negative cooling effect. That's good because you don't want the sum of these to be positive. Otherwise, you get a runaway greenhouse effect, right? So this is the negative feedback that everything pushes against. The lapse rate feedback is if you shift the atmosphere to a warmer adiabat, you actually warm up, or you raise the emission level, and you actually can cool the planet that way. This one is the relative humidity change, which if you're warming the planet, you increase the specific humidity. It's a water vapor feedback. The relative humidity stays constant. And in this context, it's a positive feedback, but the way it's described here is neutral. Albedo is just take the snow and ice, warm up the planet, melt the snow and ice. It's a positive feedback, right? Because you absorb more energy. The opposite also happens. If you cool the planet, you get more snow and ice that continues to cool the planet. So a positive feedback works both ways, warming or cooling. And then you'll notice this is the cloud feedback. And these are different models. These are 2 generations of climate models. And I put CSM2 on here, which is this dot right here. You'll notice all the spread in these things across models for 2 generations is in the cloud feedback. That's where all the uncertainty lies. This is the short wave and the long wave. You'll notice they're both generally, the short wave is more uncertain. And in particular with, this is actually the red, it doesn't show up here. It's in here. Okay, that's CESM1 in the red. CSM2 is here. There's this group of models that have really high shortwave feedbacks, and they tend to have a very high climate sensitivity. So the net feedback is here, and you'll notice there's a huge spread in that, and most of that spread is driven by the cloud feedbacks. So it's very important to understand these things. And then just shows the equilibrium climate sensitivity, the expected equilibrium warming to a CO2 doubling. And you'll notice it's increased pretty dramatically for CESM2. And then this is the effective radiative forcing. This is the aerosol, essentially. Well, no, this is the effective radiative forcing from the CO2, which is about 3.5 watts. So let's talk a little bit about the different scales of cloud processes. And one of the complexities of cloud physics is you're crossing essentially something like 12 orders of magnitude from the microphysical scale to the planetary scale. And we are usually okay if we have a lot of scale separation in our physics, because we can represent the microphysics statistically at the large scale, meaning once you start getting to the 100-meter or kilometer scale, and certainly at the 100-kilometer scale, we can start representing clouds statistically as a distribution of cloud drops. We don't have to represent each little cloud drop. As long as you have several orders of magnitude, like 6 to 10, between what we're looking at here and then where we're trying to resolve, we actually do okay. Where you typically get in trouble in modeling, and particularly for climate modeling, is in this intermediate place, which we sometimes call the gray zone, where you can't really resolve things like thunderstorms or hurricanes, but you don't have enough resolution to really represent them either. This is where we get in trouble because our parameterizations don't really work in many of those places, because they're often designed to be equilibrium or statistical, and they don't really work in that context. So what does a climate model actually try to do to represent these things? And this is going to take us to how we can replace parts of this, particularly in the cloud physics, with machine learning. And this is just a representation of this problem of doing cloud dynamics and turbulence, not just the microphysics. If we have a scene that looks like this picture here of a shallow cloud deck, which is sort of like the intro that I showed, the intro that I showed. If we're looking at that in the climate model, we might get 2 numbers out of that, right? We might get 2 layers of clouds. Those are 2 layers high. And that whole field would have to get averaged into 1 average cloud fraction per layer with 1 water content. We'd get 1 number to describe that whole complex situation. But we do that, and so we do that with a set of physics. We talk about the atmospheric dynamics. We have the surface fluxes, and this is using CAM6 as an example. There's a deep convective parameterization, a unified turbulent closure or higher order closure scheme. We have a cloud microphysics scheme, which I'm going to get into more detail about, that basically is designed to take an amount of condensed water that's consistent with the level of humidity in the atmosphere, making sure it's not saturated, and then speciate that into ice and liquid and figure out what the number concentration is and figure out the evolution of that condensate. That's informed by an aerosol model that does this aerosol cloud interactions that tells you, given a state and given the particles in the atmosphere, how many activated drops and ice crystals you should have. And then that information is actually passed into a radiation scheme that then determines the radiative fluxes and passes that back to the dynamics. So all this gets represented in the dynamics by these primitive equations. This is a hydrostatic model. There's horizontal momentum, energy, mass continuity, hydrostatic equilibrium, and basically a water vapor continuity equation. And all you have to do is solve these things at every point on the planet, every time step. It's pretty simple. There's just a few little terms in here. This is a term that gets represented at every point by all the sum of all those physical processes. These harmless looking terms are everything that's back in that time step loop and everything I just described. So this belies a lot of difficulty. And when we start talking about machine learning, you'll see we can take this as a simple problem or we can take it as a very complex problem, and it works at different levels. So how do we actually understand how to represent this? So we have the time step loop, we have all the physics, and we have these equations. There's a couple ways to do this, and just sort of going through this. There's new ways coming up all the time. I'm sure there's things I haven't heard of, so this is actually meant to prompt discussion. We can learn the results of the whole model. You can say this is the temperature now, this is the geopotential height now, or the surface pressure. What is it in 6 hours, 12 hours, 2 weeks? People do this. This is some sort of GraphCast, ForecastNet, Angu weather. Sometimes these are called foundation models. They are basically ignoring even the equations and just looking at the integral of these terms as how they evolve based on the results. That actually works when you use limited fields. It actually works pretty well, which is interesting. You can learn the inputs and outputs without worrying about what's in the middle. You can learn corrections from more detailed models. So people run high resolution models that they think are representing more of these processes. Can't run them very long, but you can run them in parallel with a low resolution model and figure out how to learn the low resolution model biases. And this can be done either for like the whole model. Here's an example of that that came out recently, or you can do it with more complex treatments. And this could be considered also learning process rates, but it's actually learning corrections for 3D radiative transfer, which is the concept that, well, it's the concept that basically we consider radiative transfer as being just in a column and don't look at what's happening from the side, but that's actually not correct. You have shadows, and particularly as the sun angle gets low, you have all kinds of other things going on. And that can be calculated, but obviously it's very expensive and it requires cross-column information. But you can learn that. And so there's been some nice work recently on this that's been trying to do that. You can try to learn these forcing terms, which is the sum of all the parameterizations. And you can do that either for individual parameterizations. This was a work on super parameterization, which I think is hard, but I think that's actually, I was talking to Pierre that there's some new work on this that's getting there. Or you can try to learn all the physics. And a lot of this work has been learning entire cloud parameterizations or using a cloud model to do that. It's been very difficult to get that stable, to sort of integrate everything and just drop these terms into the equations, particularly because if you're using a machine learning model and it's at all noisy, as this changes, the state changes with respect to time step, these things, each time step in each location can jump all over the place. And then what I'm going to talk mostly about is I think we've had more success doing this, which is learning individual process rates or multiple process rates. So there's been a lot of work looking at the radiation code where you can learn the gas optics and speed it up. I'm going to talk about work where we've actually made a bin hybrid bin bulk scheme out of the microphysics, which is very expensive, more accurate, but we can actually emulate it and then get to speeding up things again. And then Axel Seifert in Germany has some recent work where he's actually learning a microphysics code, but at the level of individual process rates, not the ultimate state, but the individual process rates in that. And he can do that with a more comprehensive microphysics and speed it up. So one of the key features is that many of these process rates are empirical anyway, and we've already tried to fit them from data, or we build them from another model. And so these machine learning techniques tend to be just more advanced versions of some of the simpler data techniques that we've always been using for many of these processes. So here's an example of learning biases from high resolution. So this is work that Chris Bretherton and some of his co-authors recently did, where they took a coarse resolution GCM and tried to actually add a neural network correction based on a high resolution version, like at 4 kilometers. And the claim is that they have state-dependent corrections, and they were able to reduce the bias, and this is biases in surface precipitation and temperature, a bit. They have a percentage, it's like 25 or 30%. And you can see, okay, those colors are less intense than these colors, but it's not really solving the problem. There are some useful comments here that I think are somewhat general, and I'll get into this, that the networks need limiting beyond what you think the inputs and outputs are. The output tendencies need constraining. The input levels, they only use a subset. And they tend to use more variables than just the function inputs. You can't just tell it what the correction is and what the state is. You have to kind of give it some idea of what latitude it's at or whether it's over land and ocean, which theoretically we shouldn't necessarily have to do. This is earlier work I talked about for learning these forcing terms. So this is an example of taking super parameterized CAM, which is embedding a reduced order idealized cloud model in the GCM and replacing the cloud physics with that. This is the neural network version, and this is the control version. So it does seem to represent, not perfectly, but it does seem to represent what is happening, at least on aggregate, in the super parameterized version. But there are some issues with stability and with the training data set when you're extrapolating to warmer SSTs. If you go to a climate change scenario, you tend to get an over extrapolation. All right, you need to go away. I don't want to see you. Thank you. So you can see here, these red lines are sort of extrapolating into places of precipitation that are not really seen on average intensities in the observations, or sorry, in the training data. So that's actually a little bit problematic with some of these, although I think it's getting better. So what I want to talk about is something we've really recently done, just drill down into improving the warm rain formation. So warm rain is a process called collision coalescence. It's sort of a continuous process where you start with a series of drops of different sizes. They're moving around or they're falling at different rates in a cloud. They run into each other and they collide and they stick together and they get bigger. And then you get these bigger drops start to fall faster, so they'll pick up other drops. And at some point, they turn into precipitation. So we typically, this continuous process, which looks something like this, we typically break into two things. We break it into autoconversion, which is when we first get big enough to start falling fast enough that we want to call it rain. It's something like 40 microns. And then we have accretion, which is this falling rain starts to really pick up cloud drops below it. So we often will break it into those two pieces, and a third piece is self-collection, which is the two raindrops will run into each other. And you see the size distributions actually evolve and grow. But we typically parameterize this by fitting to another model. So you take a model that can represent this explicitly by tracking each of these size classes of raindrops by putting them into bins, and you run a detailed large eddy simulation, and you can understand what the autoconversion and accretion is. And then you take the explicit rate and you fit it on a log-log plot with a function, and you get something like an autoconversion and accretion relationship. And what this does is this actually encodes automatically that aerosol indirect effect I talked about, which is where if you have more cloud drops, you tend to get less rain formation. That's right here, this negative exponent, right? That is your aerosol indirect effect fixed to one number based on one set of LES experiments that were run 25 years ago. And how many models use this, Greg and Marcus? Like most of them, half of them at least. There's some other methods of doing it, but they're basically the same. It's about half the models or more.
Half the models use MT2.
What?
Half of CMIP6 uses MT2, and then more people also use this one.
Really? They're using that piece of microphysics? Anyway, why would they do that? Be careful what you wish for. So basically, this autoconversion is an inverse function of drop number, and accretion is a mass-only function the way it's encoded. This is an emulator. It's an empirical fit to some other model that we call the truth. I submit that we can do better than that. And so what we've done is we've actually emulated this stochastic collection process. We're basically trying to do this more correctly. So what we do in a bulk scheme is we define some actual size distribution with a series, with a gamma function, essentially, with a series of parameters here. And what we can do is actually break that back into bins. It's a little smoother than this, but we can break that smooth function into bins. And with access to each bin, we can use this complex equation of how each size drop interacts, which is called a collection kernel, to figure out this process of accretion, autoconversion, and self-collection essentially explicitly, that we know works a lot better. But having 32 variables is much more expensive than 4. So we actually are going to try to do this. So we're going to turn the existing microphysics, what's now called the PUMA scheme, it was MG, but it's more than just Hugh Morrison and I, so we decided to change the name. And we replaced the existing bulk warm rain formulation, which is just those two equations of autoconversion accretion and another one for self-collection, with a stochastic collection kernel and a set of bins from the Tel Aviv University bin microphysics model. So what we do is we break it up into individual bins. We have clouds and rain. We run the calculation of what the stochastic collection would evolve over a time step. And when you do that, you always sort of get a bimodal distribution at the end with a minimum. We take that minimum of size, a minimum number, there's at some size, divide it back up into condensate at rain, recompose it into the moments to get an equation again, and then the difference before and after becomes our tendency. And we have tendencies for the change in liquid mass, which is equal to the opposite of the change in rain mass. We have a change in number concentration of condensate and a number concentration of rain. So there's 3 things we're actually solving for, because the formation of rain is just the mass is the opposite of the loss of liquid, just a negative. And then we're going to put that in the model and we're going to run it. And it turns out it produces really nice results, but it's really expensive. And then we're going to use a neural network to try to emulate it. So to start, this is the difference in tendencies between the bulk and the bin process rate statistics for the change in rain, the change in mass, and then the change in number for cloud water, and then the change in drop number. And this original version had 2 different networks, one for positive and one for negative tendencies. And you can see these are different, which is great. They're supposed to be different. It means the bin code is doing something different than the original model. What it means is that the existing bulk microphysics has more frequent small particles, or more frequent small tendencies. It's compensated by less frequent higher values. What that means is we're drizzling a lot more, basically, than the bin code. And that's not really correct, as I'll show. So then we went back and we built a set of emulators for this. And this version 1 was fairly complicated. We're getting to a version 2 now, which Wayne is working very hard on trying to get. It's almost there, I think. I think we're just about there. But we were basically, this is a perfect model experiment. So you put in the bin code, you run it for 2 years. It slows the entire model down by a factor of 5. It's 500% more expensive. So it's not very practical as a climate model, but we could run it for 2 years, generate a training data set, every point on the planet, process over the diurnal cycle, process over the seasons, and we can use that as a training data set to then see if we can emulate that. So we have to do a couple of things here. We filter and subsample the data to get rid of the 0 points. We transform and normalize things, put it in log space so it's more regular. First, there's a set of classifiers that are trained to classify the 0 and non-zero points based on the state. Then there are regression networks that are trained to predict the non-zero values, and there's 4 of them because this one trains the positive and negative rain numbers separately, so it's a fairly complicated set of networks that we're then going to actually run and evaluate. When we do that, so this is now the actual bin model, and this is the emulator, we get a really good representation of those points in log space. And you can see these statistics are actually quite good for this. So this is actually great, but the proof is sort of in running the climate. And so this is the mean state. This is the liquid water path, and that's the ice water path. Don't expect a lot of changes to ice water path because we're not actually touching the ice processes. We're just touching the liquid processes. What we get is this one here is the control model, basically. And then this is the emulator, or sorry, this is the bin code, which is fine. It's different. It has lower liquid water path. It is what it is. The important part is that the emulator looks pretty close to that. So the emulator actually is pretty good at reproducing what that liquid water path is. And that actually is pretty successful. What's interesting is that we do, like everything else in the model, we apply a mass fixer because occasionally we go out of sample with this, so we get negative values when we apply these tendencies. This is not good, but when we started looking in more details at this, this is a map at the lower level here of where we see the mass fixer being applied when we run the neural network. And if you're familiar with this, those bright spots are where there's no water. So we're only seeing this for edge cases. So it's not really that bad. What we're seeing is a numerical, essentially numerical instability, where the network is producing a very small value which doesn't match the numerical precision. And we have small amounts of water anyway that are just above our threshold. So we're still training, we're still reproducing some amount of water, but it's not very much. So this happens maybe 20 to 30% of the time, but it only happens in the driest region. So it's not really climatically important. And the later versions of this, we're actually correcting this by doing better filtering and training on the input data, essentially. This is one of the more interesting results, which is kind of nice. So this is the control rain rate, and rain rate is a function of liquid water path and effective radius. So what this is, and this is the rain rate. So what this says is that for high liquid water path, regardless of the size of cloud drops, you get significant rain rates. That's these tan colors here are high rain rates, these things here. This is not really physical because if you have a lot of little drops, they don't tend to fall. So when you run the bin code, you get something different, which is what's produced by a more detailed large eddy simulation model. And this happens because that regression equation for autoconversion will create rain at any liquid water path. But what happens in the bin code is you get this emergent property where you really don't see, even for high water contents, you really don't see rain rates when you have small drops. This is what's observed. It's pretty much observed that at about 15 microns, you don't see rain until you get to 15 micron cloud drops. It just doesn't happen. And that's kind of an empirical result that also emerges from these bin models. You can see basically at about 15 microns, there's a line here where all of a sudden you start getting, even with low water, you get lower water path because it's all getting depleted when you have large drops. And what's really nice is this higher order statistics is getting reproduced by the machine learning emulator version, right? So this is the nice part. We can produce what we think is a much more correct result, which is not a zonal mean. This is a really high frequency. This is looking at individual points. We can reproduce this quite effectively with the neural network, these higher order statistics. This is the precipitation intensity. You can see basically this is the control model, which doesn't produce any really high rain rates. And this is the bin code, and we're getting much closer to that with the emulator. If we don't put a fixer on it, we do get some high rain rates. So that is actually important. This is another really interesting result. If we focus on the large scale precipitation frequency, one of the chronic problems, this is the control model, of general circulation models is that they tend to rain all the time. They have a drizzle problem. And again, that's a function of how we do the autoconversion. You get any water, you'll get a little bit of rain forming. That'll have a little bit of accretion, and it'll kind of run forward. So we get way too much drizzle. There's too much frequency of precipitation, particularly in the subtropics when it's driven by the stratiform microphysics. And if you look at that stratiform precipitation, this large-scale precipitation, when we put in either the machine learning emulator or the bin code itself, we get right back to where we think the observation should be in the subtropics. This is from CloudSat, and it basically really reduces our drizzle problem in the GCM. This is very difficult to do in a general circulation model without imposing some kind of threshold on the rain rate. So we actually can reproduce that as well. So the summary of this bit is that a new, more detailed bin model of rain formation improves many aspects of the climate simulations, particularly the rain onset and frequency. I haven't shown this, but the liquid and ice balance is also slightly improved, particularly at high latitudes. We've used a set of neural networks to emulate this. We can recover the speed and reproduce the statistics. Now, this was hand-built with separate networks. The numerics are not exactly perfect. What was interesting is we're using more inputs than the initial equations. We may be compensating for some hysteresis in the system, but we are able to reproduce more effectively. We are able to reproduce this effectively with a more detailed model. So general lessons of this is that cloud processes really challenge our machine learning techniques. There's many orders of magnitude. So we're doing these log transforms. We have to filter the zero cases because we're dealing with a highly nonlinear process that has threshold effects. Initially, we treated the positive and negative tendencies separately for some of the variables like the rain number, and we had to sort out the zero cases. And we also limit the edge cases we're using. We don't use the edge cases and try to limit that on both the input and the output. Absolute conservation may not entirely be possible, but the failures are sort of in the numerical noise, so we can filter for them, and we have to filter for all kinds of other numerical errors, even in some of the general normal empirical schemes. So we do have these guardrails all over the physics. What happens when we combine the physics is we tend to actually time split the physics, these physical processes in the microphysics, which means you calculate a whole series of processes based on the same state. And then you have to combine all these tendencies and make sure you don't run out of water. So you end up correcting all these tendencies anyway when you put them together. So this tends to be not much of a problem. We basically just clip the zeros and then assemble all the tendencies in the microphysics, and it all comes out in the wash. So we do this with other methods all the time. We just make sure they don't dominate the answer. And then again, it wants more information than some of the numerics would suggest. I think in this case, the original versions actually wanted to know the altitude or the pressure. That actually helped, even though pressure does not go into those equations, and it's not anywhere in the bin scheme. It likes to know where it is in the atmosphere. That actually helps it. So what we're doing now is we're reducing the network to a simpler structure. We originally tried one network for all the tendencies. We're backing off that. We're now looking at 3 networks, 1 per tendency, and a set of filters. I don't think the full classifiers are necessary. The big news is that we've now got this all in as a standard option for CESM. There's actually there's a nameless parameter for this. Actually it's micropumas _ warm rain. KK2000 is the original parameterization. Tau runs the bin code. You can use that for training. Emulated runs the emulator. So the nice part is also the bin code comes with it, so you can always retrain it. It's easy to generate the training data. So that is going to get released in CESM 3 as an option. It's not going to be used as a standard configuration of the model, but it will be available. I'm about to go put this in another model, into E3SM, into a different but related microphysics scheme. We reuse that KK2000, as we said, in many different climate models. Can we actually train an emulator in CESM and throw it into another climate model? Will that work? Initially the thought is, well, no, but we've done it with the other empirical schemes that are just regression models. So will this work? I don't know. We're about to find that out. But we're going to put it in again where we can retrain it if we need to. And then because I'm a glutton for punishment, we're going to explore some even more detailed treatments, which may help us also when we get to ice. So if you really want to go down the rabbit hole in the microphysics, you don't even have to use bins. You can actually represent the interactions between each size drop explicitly and do what's called a super droplet formulation, which is essentially a Lagrangian treatment of microphysics. This is typically used only in direct numerical simulation, or a little bit in small scale large eddy simulation when you're simulating things on the size of meters. Right? You typically define 100 or 200 different sized super drops. They represent a number of drops, and then you define the interactions between all of them. They use a more accurate method than a stochastic collection kernel, which itself is even an approximation. We've actually explored a simple version of this. That increased the runtime by another factor of 10, so it's 500% more expensive than an actual climate model. But again, we can run that for a year, and then we can actually try to train that. So we're seeing if that actually helps us as well with some of this. Okay, so I want to finish up by talking about just some general thoughts about this and the different ways to move forward. We take a climate model at each point on the grid. We have these interactions with the physical equations, and we have the equations of motion that we're putting together. We have these equations that run those, we run that dynamics, and then we have these sort of terms in there that do the physics. What are the different methods summarizing back to do machine learning? So this is a set of tools. Some are advances or incremental, some are transformational. I'm not going to comment much about the sort of structure of science things that ML can do. General research usage, it can summarize papers for us. It can help find research, things with large language models. I do think there's some interesting approaches with task automation that we can use. There's code development and code translation, converting things from one language to another using large language models specifically set up for the tasks. Script and nameless development, I think there's a variety of things that may help automate certain stuff. I think there's some interesting pilots in generating plotting scripts from text prompts where you basically say, plot a zonal mean of this variable from this model in this way, and it'll go based on its parsing of a large language model, generate Python code to go actually make that plot for you. So thinking about how we actually do this in a climate modeling context, what do we do? One option is to learn the results of the whole model. This foundation modeling approach, the sort of that we see, weather generators that basically can predict the weather. They tend to work on limited fields. So these foundation models are called foundation models because you start with an atmospheric state. You can then figure out what the surface pressure and the geopotential height and the temperature is 10 days in advance. But if you want to understand the details of precipitation or clouds or solar radiation, you kind of have to add another machine learning model to it, right? But you can use that pre-training so you don't have to go as far backwards in actually doing that. You can also use that to sort of downscale into things like stream flow or land surface processes, which I think is going to be useful. These things are fantastic for ensembles because they run quickly. So if you want to understand uncertainty and you want to run this a lot, some of these things are good for that. So I want to think the interesting aspect, which is just conceptual, is currently the way this works is you take data, you put it into a simulation system, you develop a physical model that you think is as good as you can get, and you encode all those differential equations that we actually know, and all those tendencies we actually know, and then you just emulate the results of the physical model, ignoring all those equations and everything else, and you get a prediction. Well, how much do we need that physical model, not a simulation system? Can we just go from the data to the prediction? Should we? We know a lot about the base, we know a lot about these equations that they work. We probably shouldn't throw those out, but it's an interesting question of how far between these extremes we're actually going to go, because both of these are much faster. But the big question is this one here, that puts us out of business for doing parameterizations, right? We don't need them. Fortunately, I'll be retired by the time that happens. I'm pretty confident in that at this point. You'll probably be retired by the time that happens, I would think too. But I could be wrong on that one. Learning the forcing terms for all the physics. I know there's been experiments in this. I don't think this is going to work that well, but we can see. Learning an entire parameterization or a collection of tendencies. This is going to work pretty well for drier processes that are not extremely long linear. So things like, and learning across scales for things like gravity wave drag, I think there's a lot of potential for that. Cloud processes and things that are highly nonlinear, I think this is going to be more difficult. Obviously, you can see where this is going. I think there's a lot of potential to be learning individual tendencies for things that we really can understand and focusing on particular things in the data. But I'm sure there's things I missed in this list, right? So this work that I've been talking about, I think this is a better approach to empirical parameterizations. We already do this anyway. Machine learning is just a much better way to do it. We have the same pitfalls that we have now. There's danger of extrapolation, there's imperfect models and data, and there's this sort of process or it's time splitting approach. And then I don't know whether this is model independent. So extrapolation, we actually did do these emulators, and we did take the model once we built the emulator trained on present day. We did run it with pre-industrial aerosols with the different clouds, different cloud drop numbers in different places. We also ran it with 2 times CO2 and increase the surface temperature by 4 degrees, the SSTs, to simulate climate change. And we actually do fine. So part of it is, I think if we're training on individual locations and you get close to a physical process that we think we can understand and represent, we're not really extrapolating too far because we've seen those temperatures or that environment somewhere on the planet at some time of year, and the emulator is able to actually account for that. I think the higher up this value chain you go, the larger this extrapolation problem is going to be. Sorry. Learning corrections from more detailed models. I don't think this is going to work at a high level, like we saw with that example from the Quad-All study with trying to emulate a 4-kilometer model. I think it will work with corrections for more detailed models for things like 3D rate of transfer, individual process rates, tendencies due to individual processes. The theme is sticking closer to the physics of what we know is likely to be easier as we start this process. We're also likely to understand when it's hallucinating better. And I was talking to Pierre about this before, but I think we really haven't gone into these transformations that are going to happen in our thinking when we learn how to use the data better. There's a lot of things I think we can do with simulators that are going to really change our way to work with data and really work with assimilation processes and uncertainty analyses and models, including one of them is massive ensembles with the speed ups. The other is being able to invert models and invert data models to actually do better comparisons to observations and improve our ability to do data assimilation. I think it'll get us to higher resolution data assimilation for non-continuous fields much faster than the previous methods. But don't just take my word for it. Figure to get back to ChatGPT and let it summarize things. Again, more boilerplate. Enhanced predictive accuracy, maybe. Problem is, it's more enhanced precision, but you don't necessarily always know when it's accurate. It will provide some data-driven insights, and you do get faster assimilation and analysis times. There is the possibility of uncertainty quantification enabled if we use the networks correctly. And it just kept going for like 2 more pages with this, but I decided to cut it off there. So anyway, I think I'll stop there. So thank you.
Any questions for Andrew, starting with the early career scientists? Yeah, okay.
Hi, Andrew. Great talk. I'm wondering, I guess, as part of this bigger picture of trying to work with data more directly and maybe with like a specific example from what you were showing, you show that the tau emulator and the tau versions of CSM can emulate a cloud set.
Oh, they can reproduce the cloud set results, yeah.
But that's only if you're looking at large scale precip frequency. When you go back to
Right.
total, you see we still have a large bias, and we've now just pushed a lot more of the precipitation into convective.
Right.
I'm wondering if you can comment on, like, do you think we need to kind of destruct a bit some of these like model classifications that are incongruent with observations? Or
so yes, because for example, CSM in its latest incarnation contains 2 microphysics schemes. One of them is the one I described, which is very detailed. There is a microphysics scheme in the convective parameterization, which contains autoconversion and accretion, which is 1 line of code and 1 parameter. It is even cruder than the regression model. There are some versions that try to unify that, where you put the microphysics into the convective scheme, and then you could do the same thing where you actually do better autoconversion and accretion. So one approach is to actually push this all the way through and unify the microphysics. I think in this case, that's kind of one option. We can see if that works. Again, the convection scheme is also highly uncertain and has its own issues. So there's been attempts to emulate that or emulate the whole cloud physics as well. So I think it's going to be a little dependent on the particular case. In this case, what I described is not, in other words, you're still doing the old school method for rain formation in the convection, and that's creating the problem here. Yeah.
I have a question. Do you have
Hang on, we got microphone coming over.
do you have 2 different models for the ocean part and the land part?
No.
The interactions are different.
No, it's actually not. What's only different is the typical average drop number is much higher over land because there's more sources of aerosols. So if you actually looked at a map of number concentration of cloud drops, you would see over land they're like 200 to 300 per cubic centimeter, and over the ocean it's like 100. So the land jumps out. So I think it's one network, but it's a different part of the space because the base state number concentration is very different over land and ocean. And we don't need to tell the model we're actually over land and ocean. We started doing that, but we found we didn't actually need to. It's just a different, in other words, it's a natural tendency to be a different part of the phase space, if that makes sense.
I was just thinking that at the ocean level, you have also the ocean interaction with the air.
Right, but that comes, right. So as far as the clouds are concerned, that comes through the humidity and the turbulence. So I think we don't have to tell the emulator this, it can actually figure it out. And it's because the process is a local process that's a function of the state. It's a function of the humidity, the water content, and the drop populations themselves. It's not as dependent on whether you're physically over land or ocean.
We have time for one more question, and we have someone online. Dave, can you unmute yourself?
Yeah. Hey, Andrew, it's Dave.
Hey, Dave.
Back when you were introducing the original equation with that negative exponent, and you were describing that as the aerosol, essentially the aerosol indirect effect.
Yep.
So can you sort of characterize what the aerosol indirect effect looks like now when you've removed that equation? Is there even asking?
We did actually characterize it. The whole point of embarking on this process was to see if that would change. And unfortunately, we got a no result, which it didn't change. But it would be interesting, and it's a good point. We could go back and run this regression again on their neural network results and regenerate what that exponent actually is, which is something that actually would be worth doing to see if it actually implies that we've changed it. And I haven't looked with the latest version of the emulator to see if we've actually done anything about it, if that's evolved. But it's a good point, Dave. Thanks. We also looked at the cloud feedbacks. They changed a little bit. They actually went down because the liquid and ice balance changed because the rain formation changes in the extratropics. So this did actually reduce the climate sensitivity a bit in CESM. Marcus.
Considering that there's a fundamental issue with trying to represent all these droplets with just a few bulk variables, there is essentially still going to be uncertainty just because you can't represent the true degrees of freedom. So is there, what's sort of the plan for accounting for that uncertainty that can sort of vary from cloud point to cloud point in a sort of unordered way?
So do you mean the degrees of freedom in the gamma functions or in the bins or?
Through cloud droplet populations.
Oh, well, the whole point is, right. So the most uncertainty is when you're using the gamma function, the bulk method. Where is it? Here. There's less uncertainty in the bin representation, and there's even less uncertainty in the super droplets.
But you're always converting from a gamma.
Right. Right. So yes, there is uncertainty in that, and we're not dealing with that right now. We're just focusing on the rain formation. But there is no reason why that uncertainty couldn't be done better with something like BOSS, where you make these distributions more flexible. It would actually play with this, I think, pretty well. You just have a more complex description of the moments coming in to the scheme. So yeah, you could use a higher order representation of something that was beyond just a simple 2-moment gamma function. You could go to 3-moment. You could do something that's actually learned. You could make the moments more variable. So yeah, this could be used in more detailed models with more complex microphysics in an almost straight up way, which would be something else interesting to explore.
Great. Let's thank Andrew again. And please remember, we'll have the lead professional development session now. Thanks.